Hey friends, welcome to another edition of Math That Matters. Today we're going to look at logic and argumentation, part 3, and I think you're going to love it. There's a lot of details in here that may be a little bit boring at first, but once you see how they can be used, you're going to love it. So let me share my screen with you. And let's start out with a little game. A little game called Let's Make a Deal. Let's Make a Deal was a game show back in the 70s. You can see the host was Monty. He actually died not too long ago, which is kind of sad. The game show was pretty fun because they would have contestants that would start playing a game, and in the middle of the game, they would change the rules. And then they'd say, do you want to play the game differently? So the Monty Hall problem is a classic problem whereby there are 3 doors, and depending on the game or the day or the explanation, behind one of the doors is a brand new car. So if you can pick the door that the car is behind, you get the car. And the other two doors, there is, well, it's either a donkey behind the other 2 doors, or in some forms of the question, there was a goat. So you'd get a goat behind 2 of the 3 doors, or a donkey. So the question actually became more complicated because the contestant would pick a door, like say in this case, the contestant is picking door 3, and then Monty would say, by the way, there's a goat behind door 1. So you know that door 1 was the wrong pick. So he reveals a wrong pick to you. And then he says, you can stay with your original guess, door 3, or you can switch to door 2. What would you like to do? And so the interesting thing is, well, I guess what's interesting to me is if there's an advantage in staying, if there's an advantage in switching, or if it really, there's no advantage one way or the other, that the luck of the draw will just be that you win the car, you don't, and go ahead and sort of randomly go with what he suggests or stick with your own first pick. Well, it's kind of interesting. If you look at a simulator, which we'll go to in just a moment, a simulator would just play this game over and over and over and over, and we would just collect data. And so a simulator would give us lots of detailed, specific information about when you win and when you lose and how often that happens. But as an inductive argument, we could just take a whole bunch of data and we should say, if we know how many wins and losses happen, whether the contestant switches or stays, then that might sway our guess. Like, I think it's going to be better, or maybe it's just going to be the same to stay versus switch. Well, it turns out, I found a little simulator online here. So let's play this. Where do you want to pick? Let's pick door 2. If I pick door 2, suddenly I see that there was a goat behind door 3. And of course, that means I don't want to switch to door 3 because there's a goat there, but maybe the car is behind door 2, and maybe I picked correctly with my first guess, or I can switch to door 1 if I want to. So I think I will. I'll switch to door 1. And look at that, I got the car. What's even more interesting, though, is if you look down here, the number of players that switched, this is a very big sample, 1,581 players switched. And of those 1,581 switchers, we have 1,032 winners, which is about a 65% winning percentage for the switchers. And look, those that didn't switch had a 33.5% win. So the question that you want to be asking yourself is, based on this pretty large sample, is that enough evidence for me to decide that I think I'll switch all the time? Because really, it looks like they're winning about twice as often as the non-switchers. In statistics, there's a law called the law of large numbers, and the law of large numbers says that if you have lots and lots of data, then the percentages will align themselves with the theoretical probabilities. And indeed, in this case, it actually is to your advantage. In fact, it's twice as good to decide to switch rather than to stay. So let's take a look at that. And of course, we could get partners in play, except for this is a video. So there's lots of you out there, but right now there's none of you out there. So we just simulated that. Should I switch or should I stay? Now, then again, you may not want the car. You might want the goat. You might have an affinity for goats because you love them. You might need goats to eat your grass. Or I've actually heard that goat is the best, most healthy meat. So who knows? Maybe you'd rather have a goat than a car. I'd probably take the car. Well, here's the solution. The solution is, and the reason this is in logic and argumentation is if you think really well through these possibilities, you'll decide to switch your guess. So if you initially pick a goat and Monty shows you the other goat, you will switch to the car. Thus, you will win every time your first pick is a goat. Think about that for a minute. If you pick goat behind door A, Monty shows you goat behind door C, and you switch to car behind door B. But you could have picked door C goat, and he shows you door A goat, and you switch to car at door B. So the only way you actually lose if you decide to switch your guess is if you pick the car with your initial guess, and then you switch away from it. But you're going to pick the car with your initial guess 1/3 of the time, and you'll pick a goat 2/3 of the time. And if you pick a goat, you'll win if you decide to switch. So a good way of using logic to make a decision and win a car, unless, of course, you'd like the goat. With logic, oftentimes we make these little tree diagrams. It's called a graph. It doesn't look like a graph to you probably because you're used to functions and graphs and algebra. But in graph theory and combinatorics and probability theory and statistics and lots of other applications, including logic, we make these little diagrams. We say, well, let's play this game. We're going to consider the possibilities. I could pick the door with the car, and there's a 1/3 probability of that. And if I pick the door with the car, and I change my guess, I'm gonna lose. The probability of winning is 0. But if I pick the door with the car and I don't change, then I'll win the car. And there's a 1/3 chance of that happening. The other scenario is I pick a goat door, which there is a 2/3 probability of, and I change to the car. So there's a 2/3 chance that I get the car. But of course, if I pick the goat door and I don't change and I stay with the goat, then there's a 0% chance of winning. So twice as good a chance of winning if you pick a goat door. This is called a tree diagram, and it just routes us into different possibilities in the different scenarios, which is really helpful because sometimes logic twists your brain around. What shall we do with all of this? Oh, should we play this game again with 5 doors instead of 3 doors? Maybe in a different class. That'd be fun. Or maybe we should do the trolley haul problem, but this looks a little bit morbid, and I don't think anybody wants to play this game. It looks like no matter what, you're going to lose. But will you lose big or will you lose small? Unless the small is someone you love. All right, let's talk about mathematical statements. You're going to see little mind twister problems like this, and you can read them and play with them. The book is kind of fun. I'm pulling some of this information from a discrete mathematics textbook, which you'll see online. But fun little games to play. And what we have is if we can take the different statements and the way that the statements are arranged and the way that they're combined and apply different little charts called truth tables and principles of logic, then maybe we can solve some of these puzzles a little bit better than just being smart. That appeals to me because I'm not that smart. So if I can have little tricks that will make me, I guess, not just appear to be smarter, but able to think well, then that helps me. So I want to teach you some little tricks and some of the mechanics of logic. We start with statements. Statements are the building blocks of arguments. A statement has to be either true or false. And if you don't know whether it's true or false, you have to be able to figure that out. And if you don't have enough information to figure that out, then it's not a statement until you do. So here are some statements. 2 + 2 is 4. It's a statement. It's a true statement. 2 + 2 is 5 is also a statement. It's false. The Nile is a river in northeastern Africa. Statement. The Yangtze is a river in Japan. Statement. One of these is true and one of these is false, but they're both statements. So it's okay to say something that is false. In logic, it just will be labeled that way. And it's useful information to know when something is false. But take out the trash, not a statement. It's probably not even something you've ever heard because students have selective hearing and they decide not to hear things like take out the trash. Clean your room would be another one of those. Are you going to eat that? That's probably something that you would definitely hear, unless it's someone asking you, because nobody your age likes to give up food. Statements versus sentences. How about atomic statements? A statement that can't be broken down into more pieces of meaning is called an atomic statement, like an atom. But one that has extra parts that kind of fit together, that is called a molecular statement. So you can see down below, we've got some atomic statements, which are true or false, but they're sort of a single thing, even though this is obviously false. The moon isn't made of cheese. But then again, maybe it's not false. Maybe they've just been lying to us. Not sure about that. 42 is a perfect square. I don't think so. 21 times 2. Nothing times itself is 42. Yeah, these are all atomic statements. These are not statements. Would you like some cake? It doesn't mean that it has no meaning, but it means that we can't take something like a question and plug it into our tests for logic. The sum of two squares. What do you mean? It's an incomplete thought. It might be a part of a statement, but it's not a full statement in and of itself. Go to your room. Of course, that's not even something you all can hear either because, well, maybe at this point you can, but you don't care because you're in college and you're independent. Or so you think. 3 plus x equals 12. Not a statement. Not a statement because I don't know if it's true or not. I don't know what x is. But if I gave you an x, then it would be a statement. If x was 4, 3 plus 4 equals 12 would be a statement. It'd be a false one, but that's okay. All right, now we're going to get into putting statements together, and we're going to start looking at symbols. So when you see this symbol right here, that is the and symbol. This is read P and Q. It's called a conjunction. The upside down caret that looks kind of like a V here, P or Q. That's a disjunction. When we see an arrow like this, P goes to Q or P implies Q. Another way to read that is if P, then Q. So we're starting to learn the code for the kinds of statements that are more complex, that have meaning, and that we can test. P with the double arrow to Q is called P if and only if Q. That's a biconditional statement. And what that really means is if P, then Q. Also, if Q, then P. One means the other follows. And our last logical operator here is this little funny sideways L thing, which means not. Not P is called a negation. Now, in our other textbook that we use often, there's a little tilde here instead of the little sideways L. So we'll get used to that too. All right, let's talk a little bit more about each of those. Compound statements, a conjunction with the and. So if I say it is hot and sunny, and marries the two together. And in order for hot and sunny to be true, I'm going to evaluate if hot and sunny is true. So I go outside and I look around and I say, it has to be both for the statement hot and sunny to be true. So if it's hot but it's not sunny, then the statement hot and sunny is not true. If it's sunny but not hot, hot and sunny is not true. However, the disjunction or, P or Q, hot or sunny, could be true if it was hot but not sunny. It would be true if it was sunny but not hot. It also would be true if it were both hot and sunny. So hot or sunny pulls together either scenario, and if it's one or the other, the whole thing's true. And again, we're trying to evaluate statements as to whether they are true or not. So I sort of mentioned part of this. P and Q is true when both P and Q are true. They both have to be true for the conjunction to be true. However, P or Q is true when P is true or Q is true or both are true, but you don't need them both. You just need one or the other for the statement P or Q to be true. This one's interesting, and we'll talk about it more in a little bit. P implies Q. If P, then Q is true when P is false, or Q is true, or they're both true. That's sort of strange. We're going to have to talk about that. P with the double arrow Q. P if and only if Q is true when P and Q are both true or both false. And not P is true when P is false, because P and not P are opposites. I'm moving right along because there are just a lot of different mechanics that you can rewind the video and you can ask questions about, but I just want to cover them, and then we'll get to some interesting applications in a little bit. Conditional statements. This is really interesting, though. We're talking about P implies Q. If P, then Q is a conditional statement, and that means Q will be true if P, the condition, is met. So if we can get P, then Q will follow. If you confess your sins, then he will cleanse you from all unrighteousness. So if this is a true statement, and I confess my sins, then he, capital He, that would be Jesus, would cleanse me from all of my unrighteousness. Conditional statements. This says, if you show up for work Monday morning, then you will get the job. P implies Q. You show up for work, that would be P. We've got a little Venn diagram here. You show up for work, and if you're in circle P, you're also in circle Q. So you can look at a Venn diagram and you can kind of understand why being in P or meeting the condition of the statement will cause you to fall into Q. The then part will follow. If you show up for work Monday morning, then you will get the job. Now, think about this. When would that statement be false? In other words, if I made this statement, if you show up for work Monday morning, you will get the job. What scenario would give you good cause to call me a liar? I think if you showed up for work Monday morning and I said, you don't have the job, you would be upset, right? You would call me a liar. In fact, you would say, but you said if I showed up for work, then I would get the job. So the only situation where the statement is false is when P is true, but Q does not follow. When the first part is true, but the second part is false. That's the only way a conditional can be determined to be false, which is sort of strange because if you don't show up for work Monday morning, so if P is false, does that mean that you don't get the job? And the answer is not necessarily. If you think about the last slide with the little circle into the bigger circle, you actually could be in the bigger circle, but not in the littler circle. So the only conditions where the statement P implies Q is false is when P is true, but Q does not follow. That's very, very important. Consider the statement. If Bob gets a 90 on the final, then Bob will pass the class. When is that false? You can pause the video for a minute and answer that question. When is this false? This would be false in the case where Bob did get a 90 on the final, but did not pass the class. That would be an untrue statement. But suppose Bob does not get a 90 on the final. Suppose the first part is false. That does not then render the statement, the if-then statement, untrue. And so when the if part is true and the then part is false, that is the only time the statement is not true. Which means if the if part is ever false, then the then part never had a chance to see if it followed the if part because the if part was false. And therefore the whole statement is true. And that's called vacuous truth, which is kind of a mind twister. You have to think about that just a little bit. This is called a truth table, and we'll do lots of them during the next lesson. This will look at two parts of this statement, this implication or conditional statement. So we have P and we have Q, and then we're looking at the case where P is true and Q is true. That means Q is following P, and P leads to Q is true. Q does follow P. Q is true when P is true. Now, the second scenario, P is true, but Q does not follow. That means the statement P implies Q is false because Q is not following P. Q is false, but P is true. So that is the instance where it's false. However, the strange thing is that these other two instances where P is false, it doesn't matter what Q is. P implies Q is deemed true. This is called vacuous truth. Vacuous truth happens when it's called the antecedent, or the if part, is false. So if the if part is ever false, then the whole statement P implies Q is deemed true, even though it's called vacuous truth, because Q never had a chance to know if it followed P, because P wasn't true. Very important. So if I look at a statement like this, if 0 equals 1, then 1 equals 2, I say true. True. What? True. It doesn't seem true at all, right? Because you got something that's false, and then you have something that's false. But the if-then statement is a true statement. It's vacuously true because the if part will never be true. If 0 equals 1, never true. So we can never test that this follows this being true, because this is never true. So because this is false and this is false, the whole statement is true. In fact, because the first part is false, the whole statement then therefore is true. That's a definition that even if you can't quite wrap your head around the truth of it, you can, I guess, memorize it. If an if-then statement has an if part that is always false, then the then part, it doesn't matter if it's true or not. The whole statement is true. True or false? If 1 equals 2, then most horses have 4 legs. So do I really need to think whether or not most horses have 4 legs? And the answer is, I don't. I don't need to think that, because 1 equals 2 is false. And when a conditional statement has an if part that is false, then I treat the whole thing as true, because I never had the then part to look to a true if part and see if it followed it or not, which is sort of weird. How about this? If 1 equals 1, then 2 equals 1. Wait a second. The if part is true, but the then part does not follow. That's a false statement. How about this? If 8 is a prime number, wait a minute. 8 is not a prime number. What does that mean? That means the next part doesn't matter at all. So my statement is true. How about this? If the 7,624th digit of pi is an 8, then 2 plus 2 equals 4. I gotta think about that. The then part actually is true. It's true no matter what. The only way this can be false is if the if part is true and it leads to a then that is false. But then is always true, which means this can never be false. So that statement is true. That'll be fun to play with. You're going to like it. All right, a couple more things. Actually, quite a few more things. I've got, this is fun. This is just good stuff. So suppose I wanted to make an argument that P implies Q. If P, then Q. How do I prove that? Well, this would be true if when P is Q, if when P isn't Q, P is P. If when P is true, then Q follows. So to prove this, I actually get to assume that P is true. I get all of P, and I just have to show that it leads to Q, whether I'm doing something in mathematics or something verbally. To show that if P then Q, I assume P to be true and show that Q must follow. All right, so we also like to play with if-then statements by turning them around. So if I have the statement P implies Q, and I turn it around to Q implies P, that's called the converse. If I take P implies Q, and I flip it around, and I negate both, I would get not Q implies not P. That's called the contrapositive, which is pretty cool because the contrapositive is equivalent to the original statement. So if you have P implies Q, and we'll prove this in the next lesson, if you have P implies Q, then not Q implies not P is free to you. You can turn the statement around and negate it, and it means exactly the same thing. And we'll talk about that at a later time. The inverse of P implies Q is just negating both parts. So that is not P implies not Q. If not P, then not Q. And the inverse and the converse are not the same thing as P implies Q, just like the contrapositive is. However, the converse, P implies Q, and the inverse, not P implies not Q, are contrapositives, which means the inverse and the converse are equivalent. So clearly I cannot choose the wine in front of me. If you don't know you're a Princess Bride, then you can't pass the class. All right, so let's see what we can do with this. Here's Sue. I tell Sue, if you get a 93 on the final, you'll get an A in the class. Let's assume that what I told Sue was true. What can I conclude in the following cases? 1, Sue gets a 93 on her final. Well, if what I just told her was true, then she will get an A. Yeah. But what if Sue gets an A? Does that mean that she got a 93% on her final? And the answer is not necessarily. It's inconclusive, because I can't just turn the if-then statement around and say if she gets an A, then she gets a 93%. That's called the converse. It's not necessarily true. How about this one? Sue does not get a 93% on her final. So you're like, does that mean anything? Well, if she gets a 93%, we know that she gets an A, but she doesn't get a 93%. Does that mean that she doesn't get an A? And the answer is not necessarily. We can't say that if Sue does not get a 93%, then she does not get an A. That would be the inverse, and the inverse isn't necessarily true. It's not equivalent to the original statement, so we don't know. She might not get a 93, and she might get some extra bonus points. We don't know. How about this one? Sue does not get an A in the class. Well, that actually does mean that she did not get a 93%. Because if she had gotten a 93%, she would have gotten an A. But she didn't get an A. If she doesn't get an A, then she can't get a 93%. That's actually the contrapositive of the original statement, which is equivalent to the original. So I don't know if you enjoy all of this. I'm trying to talk slowly enough that you can pause and go back and think about it, trying to be clear, but there are a lot of things that do make sense, and there are a lot of things that seem to make sense but don't, and you have to be careful. All right, I think I'll pause. I've got some other definitions and some other mechanics, but I'm going to pause for a little bit just to make sure that you see what we're really trying to do with all of this. What we're really trying to do with all of this is to kind of untangle arguments. And I was reading in my Bible this morning, John chapter 4, and Jesus was talking with a woman at a well, and he actually was making an argument that she should ask him for a drink. So let's look at this. A Samaritan woman came to draw water, and Jesus said, "Give me a drink of water." Surprised, she said, "Why would a Jew ask a Samaritan for a drink of water?" And Jesus said, "If only you knew who I am and the gift that God wants to give you." Notice there's an if and there's an and. Jesus is using logic. "Then you would ask me for a drink and I would give you living water." The woman replied, "Sir, you don't even have a bucket, and this well is very deep. So where do you find this living water? Do you really think that you are greater than our ancestor Jacob, who dug this well and drank from it himself, along with his children and livestock?" Jesus replied, "If you drink from Jacob's well, you'll be thirsty again and again. But," a logic word, "if anyone drinks the living water I give them, they will never thirst again and will be forever satisfied. For when you drink the water I give you, it becomes a fountain of the Holy Spirit, springing up and flooding you with eternal life." The woman replied, "Let me drink that water, so I'll never be thirsty again and won't have to come back here to draw water." So what do we want to learn how to do? We want to learn to look at an argument and say, does this work? And that means that we have to take the parts of the language that have statement type meaning and see if they connect with each other. So what is Jesus really doing as he builds this argument for the woman to ask him to give her a drink? So what I did was I looked at these parts of the language and I assigned symbols. And now we'll read through the symbols, and you can see there's a little key down here to tell what the symbols mean. So Jesus says, "If you knew who I am and the gift that God wants to give you, then you'd ask me for a drink. If you asked me for a drink, I would give you living water. But the woman has a counter argument, and she says, sure, here you go, down here. You don't even have a bucket. If you don't have a bucket, remember, whenever you see an arrow, you read an if then. If you don't have a bucket, then you will not, this is a tilde, so this is a not, you will not get water from this well. Notice I distinguished water from this well from L, the living water, because Jesus is making a distinction, and he will counter her rebuttal in just a minute. So she says, if you don't have a bucket, then you can't drink water from this well. And if you can't drink water from this well, or then why should I ask you for a drink, right? Or do you? To which Jesus replies, if you drink from this well, then you will thirst again. If you drink the living water, then you will never thirst again. If you don't want to be thirsty, then you should, I'm sorry, if you, I'm trying to look up at the words and look down at my symbols at the same time. It's a little tricky sometimes. If you don't thirst again, then you will have, be forever satisfied, have eternal life. There we go. And the woman says, let me drink this water. And if you look at this, this is the contrapositive. If I don't want to thirst again, then I shouldn't drink water from this well. If I ask him for a drink, then he'll give me a living water. If he gives me living water, then I will not thirst again. And if I don't thirst again, then I'll have eternal life. And then she says, give me a drink. And he gives her eternal life. I love that. So an application, learning how to read our Bible, learning what Jesus is saying, not only to her, but to all of us. Okay, back to the mechanics, and we'll try to get through this relatively quickly. When you see this double arrow we mentioned earlier, that just means you get a double if then. It actually means that the statement P implies Q and the statement Q implies P, the converse, that they're both true. And so we could say P if and only if Q, which really means if P then Q and if Q then P. So that's kind of useful information. Oh boy, here we go. Necessary and sufficient conditions. Now this might be a little bit confusing, so I have a chart here on the next slide. P is necessary for Q means if Q then P. P is necessary for Q means if Q then P. P is sufficient for Q means if P then Q. So necessary means it has to be present, and sufficient means it is enough. If P is necessary and sufficient for Q, then P if and only if Q. Look at this chart. This will help explain it. A is a sufficient condition for B whenever the occurrence of A is all that is needed for the occurrence of B. Like if you have A, you're definitely going to have B. It's enough. But B is a necessary condition for A whenever A cannot occur without the occurrence of B. So sufficient means if A, then B. If you have A, it's enough to say B. But necessary means if A, then B. It's not exactly the same thing. So how would you fill in this blank? Hydrogen is a blank condition for water, and being a dog is a blank condition for being an animal. I would say hydrogen is a necessary condition for water. Without it, you're not going to have water. But with it, you're still not going to have water. You also need oxygen, right? H2O is water. So hydrogen is a necessary condition for water. But it's not sufficient. You need more. How about this? Being a dog is a sufficient condition for being an animal. If you're a dog, you are an animal. It's enough. You don't have to be anything else to be an animal. Necessary and sufficient. We're getting there. Other things, quantifiers, existential statements. And you'll see on the next slide that we have some symbols for these things. So there exists is this backwards capital E. And it just means you can find at least one. There is something in existence. For God so loved the world that he sent his one and only Son, that whoever believes in him might not perish, but have everlasting life. So the one and only, there exists one and only one. The other type of quantifier is a universal statement for all. It makes an assertion about everything in a particular universe inside a particular category. For all have sinned and fallen short of the glory of God. All. So this is a claim about all humans. What's kind of interesting is if you negate a universal statement, you get an existential statement. So if you say not for all, it means there exists not. Similarly, negating an existential means you get a universal. So to say there doesn't exist something means for all not. So if I have for all have sinned and fallen short of the glory of God, and I try to negate that statement, the negative of that statement is not a for all, it's a there exists. So the opposite of for all have sinned would be there exists a sinless one. There exists at least one. How would I negate the existential statement? Sometimes I get thirsty. So there exists a time where I get thirsty. What would it mean to say not that? Not sometimes I get thirsty. I guess you could say I'm always never thirsty. Or maybe just I never get thirsty. Now you'll see these funny symbols start to pop up. And when you see the capital backwards E, it means there exists. So this statement would read, there exists X such that X is smaller than 0. And it just means that there exists a number less than 0. And you can find it easily. You just say like -1. There you go. I've proven it. Whereas this universal statement and the quantifier is at upside down capital A. The way you read this is for all X, X is bigger than or equal to 0. Now, this is not a true statement because I can find something outside of that category. I can find an X that's not bigger than or equal to 0. So the negation of this is true, which is actually this right here. So the negation of this, and the negation of this is that. When you negate one type of quantifier, you get the other, but you get the not of the other. And that's why we have an X less than 0 and then an X greater than or equal to 0, because these are nots of each other, but the not of a there exists is a for all, which is kind of crazy. And that's stated here. Not for all X, some property of X is equivalent to there exists X such that not P of X. Or you could say not there exists X such that P of X, some property of X, is the same thing as saying for all X, not that property. Existential and universal quantifiers. All right, we're getting there. A couple more definitions. This is just kind of a grinded out lesson, but it's important stuff. You got to get all this stuff in your head. A tautology is a statement that's always true, no matter what. A contradiction is a statement that's always false, no matter what. And no matter what, no matter what, no matter what. That's the end of this. That's the end of it. So sometimes you have a tautology. If I say P or not P, P or not P, something or the opposite, it's true, right? Something or everything outside of the something, that's true. But if I say P and not P, something and not itself, that's always false, because you can't have something and also not that something. That's a contradiction. Tautology is always true. Contradiction is always false. I will either get paid or I will not get paid. Tautology, always true. Either Jesus is God or he is not God. Tautology. Contradiction. You can see Calvin here. I didn't do it. I never threw it. You can't prove it. I threw it. Besides, I missed. I'm like, wait a second. I think you just contradicted yourself, right? Because if you missed, that implies you threw it, but you just said you didn't throw it. Sorry, Calvin. How about this? All truth is relative. This is the theory of relativism. So that is the same thing as saying there is no absolute truth. How would we find a counterexample? There is no absolute truth. Why is this a contradiction in itself? Because I guess I could just ask the question, is that absolutely true? If it's absolutely true, we just found one. And all it takes is one counterexample to show that there exists not some universal statement like this. All truth is relative. This is sort of the argument is equivalent to there is no absolute truth, and this is a contradiction because it itself is a truth claim, which means relativism, the belief that there is no absolute truth, is a self-refuting position. Because there's at least one truth if that is to be believed. Yes, and there it is. Tautology Contradiction. This I thought was kind of interesting. It might help you with one problem on your homework. It's kind of cool. If P then Q, we can actually turn into a different statement that means the same thing, and that is either not P or Q. And that's sort of weird to think that that means the same thing. But here, if you say, let's start out with something that's always true, not P or P, but P implies Q. So not P or Q. Another way of saying it is not P or P, but P implies Q, so not P or Q. Maybe an example will help. If you lift weights, then you will be strong. That's the same thing as saying either don't lift weights or be strong. Now, you might not understand that, but think about it this way. How about either don't lift weights or do lift weights? But if you do, you'll be strong. I like it. One more example, and then I'll let you go here. Thanks for taking the time. Here it is. This is a problem on the homework. In my safe is a sheet of paper with two shapes drawn it in one color in crayon. One is a square, the other is a triangle. Suppose you believe me when I tell you that if the square is blue, then the triangle is green. What do you therefore know about the truth value of the following statements? A, the square and the triangle are both blue. Now wait, if the square is blue, then the triangle is green, and this would assert that the square is blue, which if this statement was true, then the triangle would be green. And I'm given that this statement is true, meaning part A must be false. How about this? The square and the triangle are both green. Is that possible? Well, if the square is blue, the triangle is green. It doesn't say anything about if the square is green, so B is possible. How about C? If the triangle is not green, then the square is not blue. I would agree with that, because if the square were blue, then the triangle would be green, right? I would agree with C. That's the contrapositive. D, if the triangle is green, then the square is blue. Now that would be the converse, and we don't know that that's necessarily true. So we wouldn't be able to say part D. And how about E? The square is not blue or the triangle is green. Well, if the square is blue, then the triangle is green. But if the square is not blue, I guess I could say either the square is blue or it's not blue. But if it's blue, the triangle is green. I think you could agree with that based on the lifting weights example that I just gave. Okay, well, hopefully that was as fun for you as it was for me. Here's your homework. I'll look forward to seeing you soon. Enjoy.